Hey there, just wanted to go over some of the ideas from 7.2, which dealt a lot with graphing and the transformations on exponential functions. So I just wanted to start with a quick overview of the function. So we see, if I can get this to zoom in. There we go. So here's just a general model of an exponential function. So a times b to the x would be our simple version of that. Where a is the starting value and b is the growth rate or decay rate depending on. But so here we see the shifting transformations added on that. Remember a, as long as being that starting value, that y-intercept can also represent a vertical stretch as long as a is bigger than 1, or can represent a vertical compression if a is somewhere between 0 and 1, so some sort of decimal or fraction. So that's how we talk about the transformations in regards to a. And then h would represent our horizontal shifts. Remember that one's a liar, so if it says plus 2, that's actually going to move it to the left 2. If it said minus 3, it would actually move to the right 3. These are pretty hard to see on the graph when we do those, but we can identify them pretty easily visually in the equation. And then k represents the vertical shifts. And these are usually pretty easy to see when we took that whole graph and move it up or move it down. Remember, this will affect that asymptote, which is the line that the graph is going to get closer and closer to, but never touch. So as we shift that whole graph up or down, it will also shift the asymptote. So let's see here. So to start off with a simple one, so the function y equals 3 to the x is shifted 4 units up. Write an equation for that transform function. So I'm just going to start off with our function. So y equals 3 to the x. I want to shift it 4 units up. So remember, that's that k value, which is at the end. So all I have to do is add 4 to that, and that'll shift it 4 up. So, and the idea is, when we go from our graph, looks something like this, where it's heading off to the left really low forever. Remember, it should be getting closer and closer to the x-axis, but it's really hard to draw. So instead we draw it parallel to the x-axis, because that's our asymptote. And so that'd be y equals 0. So you would dash that in and label it with the equation, y equals 0. Then we go to this transform function, which is being shifted 4 units up. And so it takes that asymptote and it shifts it to y equals 4. And then the graph would look something like this. Same shape, everything else, just same steepness and all that. Just would go like that. So looking at the domain and range of that new function, it's going to go left forever. It's going to head off towards negative infinity. It's going to go right forever, so let's head off towards positive infinity. Our range, however, will change. So the lowest value, low to high, right, is going to be 4, but not quite 4. So we're just getting closer and closer to 4 as we head off to the left, but not actually going to touch it. And then it will go up forever. So the only thing that changed here is from the original function that this would have been a 0. Now it's a 4. So okay, so that's that. Oops, this thing. Write an equation for this exponential function. Again, I want to write in the form y equals a times b to the x. That's what an exponential function should look like. So I need to know the starting value, our y-intercept, and I need to know the rate of change, the growth rate, decay rate. So our starting value is the y-intercept, pretty easy to find, 0, 6. So that's going to be 6. And our rate is going to be found by looking at how we're changing. Always take the later point, which would be this one, and divide it by the earlier one, which would be the 06. So here, of course, 12 divided by 6 is 2. So that's going to be 2. So y equals 6 times 2 to the x. Remember, we cannot simplify that as 12 to the x or something like that. So just y equals 6 times 2 to the x is your function. Let's see. We have this here's equation. So y equals 4 times 8 to the x plus 2 power. minus 5. Identify the transformations from this to that. So I want to hit everything that's different. So like this has a 4 that the other one didn't have. It has a 2 the other one didn't have. It has the minus 5 the other one didn't have. So I want to talk about all those. Doesn't matter what order, but I'll just go in order that I see them. So the 4. So that's our vertical stretch or compression. It is bigger than 1, so it's a vertical stretch. So this graph would be steeper than the original one. Then we move to the 2, so that's where our horizontal shifts are up in the exponent. That's our liar. So this is going to shift to the left 2. So shift, make sure you have a verb there. And then a direction and a distance. And then the minus 5 against our vertical shifts. We trust that guy. So that'll be shifting down. Verb, direction, distance. Okay. That is that. Talked about all 3 things. Describe how the transformations impact the domain and range. So if we stretch a graph, just a normal graph, it's not going to change anything. So if we just, or if we compress it, as far as domain and range goes, if we just have some function, it's doing this, and we make it, stretch it higher, so it's still going to go left forever, still going to go right forever, still going to go, head towards 0 as it heads off to the right, just going to be a little bit higher, but it'll head off towards 0, and it heads up to the, heads off to the left. And it heads to the right, it'll still go up forever. So domain and range don't get changed by stretches or compressions. Shifting the graph left or right also, so if we just take that, imagine copying this black graph and just moving it to the right a couple. Still going to head towards 0. Still going to keep heading off to the right forever. Still going to go left forever. Still going to go up forever. So that didn't change the domain or the range either. And then we look at the shifting up or down. So if I shift it down 5, so oops, I guess we weren't doing something like this. So still heading to left forever, still heading to the right forever. But the lowest value did change. So it's going to head towards 5, but then still go up forever. So so the only thing that's actually affecting anything here is the shift down, and it's only affecting the range. So the domain will remain the same. And that's at negative infinity to positive infinity. But the range will now be -5 to infinity, not 0 to infinity. So there's how it will impact it. Let's see what else to talk about. So we have 3 graphs here. Which one matches each function? So just quickly glancing at the functions, seeing a lot of -2s, so that's not really going to be a way to tell things apart. Here I got a negative. Is there one that's looking like a reflection? We haven't really talked about that much, but we've talked about reflections in the past. The thing I noticed that's different in the functions is 2 of them are 1/3 and one of them is 3. So that's definitely going to be something to pay attention to. We have our b value being 1/3. That represents decay. That's less than 1. And so decay functions start high on the left and then get closer to 0 on the right. Whereas the 3 represents growth, since it's bigger than 1. And so growth starts low on the left and then gets higher on the right. So it looks something like that. So that probably be the quickest thing to determine, what's going on with which of these graphs is growth. And so I would notice that H looks like it's growing. Right? As far as what's matching here. Notice that they all have the same asymptote, the same line that they're all getting closer and closer to. That's because they all have this k value of -2. So we're getting closer and closer to y equals -2. So that leaves B and C. So F looks a lot like this, right? Ours is starting high on the left and going down, closer and closer to something on the right. Whereas G has that reflection, right? That vertical reflection. So we'd expect it to look something like this, right? Reflecting over that x-axis. And so that's what we see going on here with B. Right? So notice how it starts really low on the left side and then grows, but doesn't grow forever on the right. It has kind of a limit of its growth. So I'm saying A, and then B, and then C. I think there's just one last problem here I want to go over. Amount of medicine contained in a patient's blood H hours after it was consumed can be modeled by the function M. So it looks like M for medicine. So the medicine as a function of the time, hours, 200 times 0.79 to the H power. Use the function to complete the table. So just evaluating that, it's pretty straightforward. I'll probably round to I'll say the nearest whole number as I'm calculating this, but I'm going to take 200 times 0.79 to the 0 power. And that should be 200 because that's our starting value. So that should match that perfectly. Our 0.79 to the 0 power is 1. Anything to 0 power is 1. So 1 times 200 is 200. 0.79 times to the first times 200 is 158. 200 times 0.79 to the second is 124.82, so I'm just going to say 125. And to the third power, 98.6, blah, 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 so I'm just going to say 99. Does the function model exponential growth or decay? So how I tell that is just by looking at the B value. Is it less than 1 or is it greater than 1? And that is less than 1. So remember, B cannot be 0 or less than 0, which would be negative, but it can be less than 1. Explain what the 0.79 means in context of the problem. So thinking about that as being decay, kind of the wrong way to think about this would be that means that we're losing 79% each time. What this actually means is that we're keeping 79% of the medicine in our bloodstream as the hours pass. So let's see, each hour, your body has 79% of the medicine that it had the hour before. So it's not losing 79% per hour, it's keeping 79% per hour. And so if we kind of think about what that means, like if we're keeping, like what are we losing? So if we take 100 minus 79, we get 21. So what we're actually doing is losing 21% each hour. So a different way of saying that is the amount of medicine in your body decreases by 21% per hour. So I'm really careful about that, how to interpret that value there. Yeah, especially in the case of decay, it seems to be a bit more confusing, what I've noticed over the years. Hopefully this helped a little bit. Hope you have a good day.